Bloodstains are messy, and we've been trying to make sense of them since 1895. Bloodstain evidence is critical. There have been some cases where one single splatter of blood has made the case. However, new research shows that some models detectives are using to interpret bloodstains may be out of date, leading to faulty conclusions about how a crime was committed, or worse, incorrect verdicts in the courtroom. This video will hopefully show you my experiment on understanding the way blood behaves on different surfaces. Firstly, let's look at exactly what is happening when a bloodstain forms. This is a single drop of blood, falling vertically through the air, about to make contact with a hard surface. As it falls, cohesive forces between the molecules cause it to coalesce into a sphere, which carries momentum downwards due to the pull of gravity. When it lands, the impact creates pressure, which diverts the drop's momentum outwards, causing it to spread rapidly across the surface. Eventually, the same cohesive forces between the molecules stop the blood from spreading outwards, and will actually try to pull it back into a sphere. What prevents this is a phenomenon called pinning. When the blood stops spreading, microscopic irregularities in the surface will latch onto the edge of the fluid, effectively pinning the edge to the surface. Where the edge gets pinned will eventually form the perimeter of the stain when the blood dries. Because blood is a fluid, it obeys the laws of physics, which means detectives can be confident that it will always behave this way in similar conditions. Except, sometimes it doesn't. Now, before we get into the blood, let's have a look at water on different surfaces. Here are 3 drops falling onto a glass surface. In each case, the glass surface is the same, but 2 of them have been treated with hydrophobic coatings. Here's what happens when a drop of water falls onto a clean, untreated glass. This glass has had an acrylic coating applied to it, and this glass has been treated with an anti-fingerprint coating. It's immediately obvious that a drop of water behaves differently depending on how the surface it impacts has been treated. But water is a very simple molecule. With blood, it's not like that. It's a complex liquid. It's a combination of proteins and blood cells, which lead to a very different type of behaviour. Now to the experiment prep. Having been unable to drain my own blood, I had to substitute it with pig's blood, which is very similar to human blood, except it will never exactly mimic human blood due to erythrocyte properties differing among species. This is the experiment setup: my mother's laptop stand, 2 identical cups, the dropper and the holder, and paper to block out shadows. So, how important can a single drop of blood be? Turns out, very important. One key question at crime scenes are: was the victim standing, sitting, or lying down when assaulted? And the size of a blood stain can often answer that. According to current research, 2 drops of blood that falls from the same height onto the same surface will leave the same size stain. But what if 2 drops fall from the same height onto the same surface, but some parts of that surface are coated differently than others? Let's say you have a wooden floor, and if you've just waxed it, you might not be able to distinguish between the waxed floor or just the pure wooden floor. There could also be spots missed. I have 3 planks of wood with me: normal wood, burned wood, and wood with a hydrophobic coating on it. I'll be taking you through how and if the blood splatter chemical properties reacts differently when it comes into contact with different surfaces. Here we have a blood drop onto untouched wood. The blood droplet's characteristics match research. It pushes outwards once it hits the surface, then pins and doesn't do any other changes. This is the burned wood. The burned wood was really interesting. As it makes contact with the surface, when it should pin, it doesn't. Instead, it recoils off the wood, trying to use cohesive force to bring it back into a sphere. However, adhesive force on the first drop forces the blood drop to not fully bounce off the wood. So, let's add a second drop into it. As the first stop settles back down and stops movement, I add the second drop into it. Once again, when it should pin, it doesn't. It recoils even further off the wood. Then cohesive force brings it back into a sphere and makes contact with the wood again. this would leave two completely different dried stains from the normal wood to the burned wood. Still on the burned wood with an uneven surface. As the blood drops, once again it doesn't fully pin. However, it does latch onto those microscopic irregularities in the surface, which would cause the drop to leave a different size and shaped stain. Here is the wood with the hydrophobic surface on it. The blood drops, it pins and leaves a stain as if it was normal wood. I was surprised by this behaviour, so I did a test with the same hydrophobic coating on glass with water. When the water drops, it does no recoiling and drops as if it was on normal glass, which means the $8 hydrophobic coating from Kmart didn't work. The summary is, the burned wood, uneven wood and normal wood would all leave 3 different blood stains, which is not accounted for during investigations. Now, obviously my findings are too small and early to reach the courtrooms, but it's at least making my mind curious and I'm sure yours too. Now, I'd still like to run the experiment with a proper hydrophobic surface to see the outcome, so here are some things I could do to improve for next time. If on wood again, have a proper hydrophobic wood wax and not an $8 Kmart spray. Using a medical syringe which doesn't have room for oxygen to creep in, as my dropper was plastic, some drops weren't pure blood and they were filled with oxygen. Lastly, obviously a better camera would have helped with the experiment as my iPhone was pretty difficult to film on and it doesn't have the best quality.